shaft is optimal, but this section needs undercut of the boring tool. So these designs we are avoiding when optimizing. And also we are checking the mode shapes of the rotor for each design iteration. For that we are using the tool RotFem. It is an open source tool. Each design iteration has a finite element model, and we are calculating the mode shapes of the model and ensuring that the sensor and the actuator are on the same side of the node, such that there is no 180-degree phase shift between our measurement and our actuation. So these are some of the iterations that are being done. For optimizing, we are using Monte Carlo sampling. We are using an in-house sampling code because we are having constraints that depend on the previous design sample. So we have developed an in-house sampling code. Only the feasible space that can be manufactured is sampled. There is a 1 mm step size between successive iterations to reduce the complexity. Shaft OD we are not changing, it is fixed. ID is subjected to manufacturing constraints that I explained earlier. Section length is varied subject to minimum requirement. Say for sensor targeting I need 10 mm, I am keeping 10 mm as a minimum length and then optimizing on the higher side. So after doing these iterations, we have arrived at a rotor design that is having maximum polar moment of inertia, minimum weight, and ensures that the sensor and the target don't have 180-degree phase shifts between each other. This is the last. So through this Monte Carlo sampling, we have obtained an optimum shaft, 7.1 kg weight, 0.03 inertia, model frequency. Right now we are operating only at 4000 RPM, so there is a huge separation, so that doesn't matter right now. And the design process has been automated. Only disadvantage in this approach is that each constraint needs to be programmed in the sampling routine, but manually. It is not like we give an ID, upper bound and a lower bound, and the optimization is automated. So this is the final rotor cross section that we have arrived at. This is under fabrication right now. Any questions? Any questions?
AMB they also use auxiliary bearings. Is there any need for auxiliary bearing?
Yes.
That is there.
Yes, we have this section, bottom aux bearing. This is the region where auxiliary bearing comes. In our current test rig, we are using a phosphor bronze bush in that area. Actual rig that is going to get higher RPM will be having rolling element bearings. Yes. Right now it is a bush.
What is the specific application for which you are doing shape optimization? Because it depends on the specific application.
Right now this rig is to demonstrate stable levitation in the presence of gyroscopic precession and mutation. Once controller is proven using this rig, same controller will be used for a flywheel energy storage system for AOCS application.
What controller?
This algorithm is LQR with Kalman estimator. Controller is a DSP board, STM30.
DSP.
Yes.
Any other questions, sir? What is the energy required for this? What is the total energy required for
Powering the AMB, we have not calculated. This is a ground-based tree, but thumb rule is AMB uses 1/3 of the energy consumption of the equivalent load supporting journal bearing, oil lubricated journal bearing. Power consumption, including the electric power consumed by the controller and the actuator, is 1/3 of the journal bearing. So it is always advantageous from energy point of view to go to a magnetic bearing, provided the initial cost is absorbed.